Every whole number right triangle comes from squaring a single lattice point. Watch the blue dot at 2, 1. Square it and it jumps to 3, 4. Those become the legs of a 3, 4, 5 triangle because the dot's original distance from 0 was square root of 5, and squaring that distance gives 5. Try 3, 2. It lands at 5, 12, and its distance becomes 13. 5, 12, 13. Try 4, 1. 15, 8, 17. These familiar triangles are falling out of one motion. Take a grid point and square it. And here's the ridiculous part. Every primitive Pythagorean triple appears this way. Every single one. The grid point may swap the legs or change its sign, but it's there. As the input dot moves around, squaring doubles its angle and squares its distance. So the grid seems to stretch and twist into a spiral-shaped machine. I stared at this for a while before realizing the triangle was hiding in the motion itself. The question is why squaring a point can manufacture a right triangle, and why this machine never misses one. Keep your eye on the yellow distance. That's the part quietly doing almost all the work. The yellow distance becomes the hypotenuse because a point like 2 plus I carries two pieces of information at once. Its horizontal coordinate is 2, its vertical coordinate is 1. Mathematicians write that as 2 plus I, where I is the direction that squares to negative 1. Honestly, that sentence sounds more suspicious than it is. Now square the whole thing. 2 plus I times 2 plus I gives 4 plus 4I plus I squared. Since I squared is negative 1, the result is 3 plus 4I. There are our legs, 3 horizontally, 4 vertically. Meanwhile, distances multiply when complex numbers multiply. The distance of 2 plus I is square root of 5. Squaring the point squares that distance, so the new distance is 5. That forces 3 squared plus 4 squared to equal 5 squared. The same calculation with a general grid point m plus ni gives m squared minus n squared horizontally, 2mn vertically, and m squared plus n squared as the distance. There's the whole generator arriving before we've had to memorize it. But a generator that produces triples is only half the claim. Plenty of machines produce some good answers and quietly ignore the rest. Why should these three expressions catch every primitive triple? First, we need to separate the triangles that carry new information from enlarged copies. 6, 8, 10 is 3, 4, 5 wearing platform shoes. Divide all three sides by 2, and the smaller triangle comes back. 9, 12, 15 shrinks by 3. A triple with no common factor is called primitive. Slightly clunky word, useful idea. If we can generate every primitive triple, multiplying all three sides by any positive integer gives every other one. So focus on a primitive triangle with legs A and B and hypotenuse C. One leg must be even. If both legs were odd, their squares would each leave remainder 1 when divided by 4, making C squared leave remainder 2. Squares never do that. If both were even, the triple wouldn't be primitive, so exactly one leg is even. We'll call that one B. Also, C has to be odd. This tiny parity check is doing more than housekeeping. It tells us that C plus A and C minus A are both even, which means we can split the triangle's equation into two whole number pieces. That split is the trapdoor. Once it opens, the mysterious M and N don't have anywhere left to hide. Here's the trapdoor opening. Start with a squared plus b squared equals c squared. Move a squared across, and b squared equals c squared minus a squared. That difference factors into c plus a times c minus a. Because c and a are odd, divide both factors by 2. We get b over 2 squared equals c plus a over 2 times c minus a over 2. Now these two factors share no common divisor. If they shared 1, it would divide both their sum, which is c, and their difference, which is a. That would contradict primitiveness. So we have two coprime positive integers whose product is a perfect square. That can only happen if each one is already a perfect square. A prime factor can't sneak from one side to rescue an unmatched exponent on the other, because the sides share no primes. Therefore c plus a over 2 equals m squared, and c minus a over 2 equals n squared. Add those equations, and c becomes m squared plus n squared. Subtract them, and a becomes m squared minus n squared. Multiply them, and b becomes 2mn. The formulas weren't a lucky invention. Any primitive triple gets cornered into them. That proves the machine catches everything. Well, algebraically, visually, we still haven't seen where the spiral comes from. So any primitive triple has an address m comma n. The address has rules. We need m greater than n. Otherwise, m squared minus n squared isn't a positive leg. We need m and n coprime, or their common factor leaks into every side. And they must have opposite parity, one even and one odd. If they're both odd, all three generated values share a factor of 2 after the dust settles. Take m equals 2, n equals 1. Good address coprime. Opposite parity. Out comes 3, 4, 5. 3 and 2 gives 5, 12, 13. 4 and 1 gives 15, 8, 17. 4 and 3 gives 7, 24, 25. Now try 3 and 1. They're both odd. The machine gives 8, 6, 10, which shrinks to 4, 3, 5. Same primitive triangle, duplicated in a larger costume. Try 4 and 2. Shared factor 2. We get 12, 16, 20, another scaled copy. The restrictions remove those echoes. This means primitive triples correspond exactly to visible blue grid points above the diagonal, with shared factor points and same parity points crossed out. The surviving points look sparse and irregular. Yet when squaring twists them outward, something oddly organized appears. To see it, we need to stop thinking of m and n as two separate integers and watch their direction. The direction of m comma n determines the triangle's shape. Its size comes from the distance. If we divide the generated triple by its hypotenuse, the triangle shrinks onto a unit circle. The point becomes x equals m squared minus n squared over m squared plus n squared, and y equals 2mn over m squared plus n squared. Those coordinates satisfy x squared plus y squared equals 1, so every normalized Pythagorean triangle lands on the circle. For 2, 1, the point is 3/5, 4/5. For 3, 2, it's 5/13, 12/13. Every coordinate is rational, and every rational point on the circle, apart from one harmless endpoint, comes from a rational slope, n over m. This is the same completeness theorem wearing cleaner geometry. Watch the ray through m comma n. Its angle is theta. Squaring doubles that angle to 2 theta. Then normalization drops the point onto the unit circle. So the input wedge between 0 and 45 degrees unfolds across the entire upper semicircle. A small turn in parameter space becomes twice the turn in triangle space. The circle is where all possible shapes live. The lattice decides which shapes have whole number sides, and now we're one step from the spiral. Put the discarded size back while keeping this doubled angle. There's another way to watch the same wrapping, and this one makes the parameter feel almost physical. Put a pivot at -1, 0, on the unit circle. Draw a line through that pivot with rational slope t. Wherever the line hits the circle again, both coordinates are rational. Set t to 1/2 and the second intersection is 3/5, 4/5. That's the 3, 4, 5 triangle. Set t to 2/3 and we reach 5/13, 12/13. If t equals n over m, solving the intersection gives exactly the formulas we already found. The line turns, and its second intersection runs around the circle. Every rational slope gives a rational circle point. Run the argument backward, and every rational circle point gives a rational slope back to the pivot. Nothing slips through. I got the direction of this line wrong the first time, and produced the reflected points for about 20 minutes, so if the signs feel mildly cursed, they are. Reflection only swaps an orientation. The triangles survive. Now imagine increasing the denominator limit and drawing every allowed rational slope. The circle fills with more and more Pythagorean shapes. They never become continuous, but they become dense. Between any two Pythagorean shapes, there's another one. The spiral we want is what happens when each of those directions is allowed to keep its original integer radius. Now put angle and size together. An input point m plus ni has radius r and angle theta. Squaring sends it to radius r squared and angle 2 theta. That rule bends any outward path through parameter space into a faster outward path in triangle space. If our blue point traces a spiral while passing lattice directions in order, its square traces another spiral, stretched outward and turned twice as fast. At every lattice hit, the output coordinates are the two legs of a Pythagorean triple, and the output radius is the hypotenuse. This is the hidden spiral, I mean. It isn't claiming the integer outputs, sit on one perfect decorative curve. The exact points form a discrete family. The spiral is the continuous machine underneath them. Radius gets squared, angle gets doubled, and the valid lattice moments light up as triples. Keep your eye on one blue point as it passes 2, 1, 3, 2, 4, 3, 5, 4. Its outputs are 3, 4, 5, 5, 12, 13, 7, 24, 25, and 9, 40, 41. Those lie farther out while their normalized shapes creep toward a flat 45-degree triangle. Change the route through the input lattice, and you visit the triples in a different order, but every valid address is still waiting. The screenshot picture is this: input lattice, curling squaring flow, and the Pythagorean endpoints glowing at the other side. That picture also explains which triangles are skinny and which are almost isosceles. If n is tiny compared with m, the input point sits close to the horizontal axis. Squaring keeps the output angle small. One leg is short, the other is nearly the hypotenuse, so the triangle looks like a needle. Take 10, 1, 99, 20, 101. If n creeps close to m, the input angle approaches 45 degrees. Squaring pushes the output angle toward 90 degrees, which again makes one leg small. After we choose an orientation, the balanced right triangles happen in between, when the doubled angle approaches 45 degrees. That means the input slope n over m should approach tangent of 22.5 degrees, which is square root of 2 minus 1. There's our first irrational number sneaking into a story about integers. Rational approximations to square root of 2 minus 1 produce Pythagorean triangles, whose legs are extraordinarily close. 70 over 169 is one such approximation, and it generates legs 23,661 and 23,660, consecutive integers. The hypotenuse is 33,461. The lattice can get arbitrarily close to the ideal irrational direction without ever landing exactly on it. So whole number right triangles can become almost perfectly balanced but never perfectly balanced. The reason they approach so efficiently leads to another machine hiding under this one. Triangles whose legs differ by 1 satisfy a very strict equation. Put the odd leg at x and the even leg at x plus 1, then demand x squared plus x plus 1 squared equals c squared. Rearranging leads to a Pell equation, one of those integer equations that looks like it should have maybe 2 solutions and then produces an infinite family because math enjoys hiding trapdoors. The small examples begin with 3, 4, 5, then 20, 21, 29, then 119, 120, 169. Each solution breeds the next. In parameter space, the corresponding addresses are 2, 1, 5, 2, 12, 5, 29, 12, 70, 29, and so on. Notice the recycling. Each new pair uses the previous numbers, following a fixed recurrence. Their slopes close in on square root of 2 minus 1. Under complex squaring, those addresses become triangles whose two legs differ by exactly 1. On our spiral picture, they form a recognizable ladder of highlighted points marching outward toward the balanced direction. The gaps explode, but the shape converges. So the spiral has families inside the family: near flat triangles, nearly balanced triangles, fixed leg families, fixed difference families. The generator gives all triples, while extra number patterns choose special paths through them. There's an even stranger organizational trick. You can grow every primitive triple from 3, 4, 5 using only 3 moves. Start with 3, 4, 5. Apply one of 3 integer transformations, and you get 3 new primitive triples: 5, 12, 13, 21, 20, 29, and 15, 80, 17. Apply the same 3 moves to each child, and the branches continue forever. No repeats, no missing primitive triples. This is the Berggren tree, which sounds like a brand of flat pack shelving, and visually that's honestly close. Each move is a matrix acting on the column A, B, C. The entries look a little arbitrary when written down, so I'd rather watch what they do. One branch makes the triangle thinner, one moves it toward balance, one flips which leg dominates while increasing the size. All preserve a squared plus b squared equals c squared, and all preserve primitiveness. Run the transformations backward, and every primitive triple except 3, 4, 5 has exactly one parent with a smaller hypotenuse. Keep reversing, and you must eventually reach the root. That's why the tree contains everything exactly once. The complex square picture and the tree picture are 2 maps of the same country. The spiral organizes triples by parameter, direction, and radius. The tree organizes them by ancestry. Overlay them, and each branch becomes a crooked path winding through the squared lattice. Our nearly balanced Pell family is one especially clean branch. 3, 4, 5 was the recurring character all along, apparently reproducing when nobody was looking. Once triples are lattice addresses, we can estimate how many fit below a size limit. A triple's hypotenuse is m squared plus n squared. So asking for hypotenuse at most c means asking for valid parameter points inside a quarter circle of radius square root of c, restricted below the diagonal. The area of that wedge grows proportionally to c. Then we keep only coprime points of opposite parity, which removes a fixed fraction in the long run. Primitive triples therefore arrive at a roughly constant rate as the hypotenuse limit increases. The precise main term is c over 2 pi, so below 1000 we expect around 159 primitive triples. The exact count wiggles around that estimate because circles and square grids never cooperate perfectly. That wiggle is part of a much deeper lattice point problem. If scaled triples are included, each primitive one contributes copies at twice, 3 times, 4 times its hypotenuse until the limit cuts them off. This adds a logarithmic boost. The clean visual generator has quietly turned into a counting device. Geometry tells us the growth rate before we list anything. And because the parameter points become dense in direction, large triples eventually approximate every possible right triangle shape. Pick a shape on the circle. There are infinitely many whole number triangles crowding arbitrarily close to it. The machine fills shape space while staying completely discrete. So here's the finished machine. Choose a surviving lattice point m, n, above the axis, below the diagonal, coprime, opposite parity. Read it as the complex number m plus ni. Squaring doubles its angle and squares its radius. The output coordinates are m squared minus n squared and 2mn. Its distance is m squared plus n squared. Those are the two legs and hypotenuse of a primitive right triangle. Every primitive triple has exactly one such address after we settle which leg is even and ignore signs. Multiplication supplies all the scaled copies. Normalize the outputs and they become rational points wrapping densely around the unit circle. Follow special rational approximations and you get Pell ladders of almost isosceles triangles. Follow the 3 ancestry moves and you get the infinite Berggren tree. Same objects, different flashlights. I like the spiral view because the formula stops looking manufactured. Squaring physically turns direction into triangle shape and distance into hypotenuse. The integers just decide when the moving point clicks onto the grid. But here's the loose thread that still bugs me. Squaring works so perfectly because a sum of 2 squares is a distance in the complex plane. For whole number boxes, we'd want 3 squares adding to a square. There's no equally friendly 3-dimensional number system where multiplication preserves length and behaves exactly like this. Quaternions get close, then add a 4th dimension because apparently 3 was too convenient. So the next question is whether integer right boxes have their own hidden motion, or whether this spiral is a trick that only the plane gets to keep.